All right, so we've been working with matrices, right? That's the objects we've been working with. And we've seen a little bit how a matrix can represent a lot of different types of things, right? We think of them as representing linear equations primarily, right? And we've learned some tools for solving them and determinants and inverses and sort of how to operate that with them as objects, right? And so in 4, we're introducing something called a vector. And we like to have a geometric understanding of what a vector is to help us with our algebraic work with vectors. And all a vector is it's a directed um, line segment. When we look at vectors in R2, so like the plane. Um, So what we'll see later on is that a vector can be generalized to a number of other objects, but we can consider at least this kind of base case to help us get a sense of how they work. And that thinking will then extend to all of these other cases with vectors. So we typically think about orienting the vector at a starting point, the origin, and it's directed outward. And in R2, we usually are going to represent a vector. Since we assume it starts at this origin, we can represent this direction by just using its terminal point, which is this, again, could be X and Y, but we're going to call it typically X1 and X2, where this is my X1 value and this is my X2 value. Think of that as XY. Think of that as a point in a plane if you want to, but it's really when we would have seen like this point, say 4, 2 before, we would have considered that as just like a point in the plane, but here we're looking at it as a vector in that it's really representing the terminal point of this directed line segment. So it's a line segment with both direction and magnitude, right, or length. And so there's some general properties of vectors here. I think the most interesting one is so we'll often represent vectors, sorry, with this U with a little line over the top. You could also represent it with like a bold U. It's a little harder to do a bold U when you're writing. So this little vector on top is kind of an easier way of keeping track of that. But you'll see the book uses a boldface U to represent a vector. So I think the part, U equals V if the components are equal. Say if U is X1, X2, and V is V1, V2, then X1 has to equal V1 and X2 has to equal V2. So all that says is two vectors are equal if their components are equal to one another. The corresponding components are equal to one another. No shock there. But I think geometrically the most interesting part here is that if you add two vectors together, you're going to get this X1 plus V1 and the X2 plus V2. So you add their components together. But geometrically, what that looks like is that if you have, if we're calling this one U, and say this vector here is V, if you add them together, what you're really doing is you're adding, you can look at it visually by sort of going out here to U and then taking that corresponding vector V from this new starting point. And what that creates is this kind of parallelogram, right, where this is U and this is V, and the new vector, the sum, goes out to this terminal point, U plus V. So geometrically, when we're thinking about adding two vectors together, we can kind of think about adding these vertical components, right? The vertical component of v added onto the vertical component of u, and then adding these horizontal components, and that's going to get us to our new vector. So we have vector addition. We also want to make sure we understand scalar multiplication. So scalar multiplication, we've seen scalars when we're working with matrices, right? That's typically a real number for us. So a scalar times a vector v, we're going to multiply the components of v by c. And possibly no surprise there. That's really how vector multiplication worked with matrices, or sorry, scalar multiplication worked with matrices, and it's also true for vectors. Also note that sometimes instead of parentheses here, because that kind of makes it look like a point, we will sometimes use these triangular brackets to represent the vector. For us, it's pretty clear, so either one of those will work. I'll probably usually use parentheses, but if you see that, don't be alarmed. It really means the same thing. So we have sort of these standard operations with vectors. We can add them together and multiply them with scalars. We can subtract them. Let's just look at some. Maybe it's worthwhile to list these down. So u plus v. So if these are vectors, when we add those together, this equals another vector in the plane, and that's called closure under addition. So closure just means like when you add two things together, you don't get somewhere else, right? So if I add two whole numbers together, I get another whole number, right? That's closed under addition. So vectors are closed under addition. They also are commutative. U plus v equals v plus u. That's the commutative. There's an associative property too. If we have three vectors like this, you can add the first two, and that's the same as adding the second two first. And it shouldn't be a surprise just because of how vector addition is defined, right? You're just adding numbers together here, the components. So, that's going to make it commutative and associative because that's how numbers work. We also have an identity, an additive identity. U plus the zero vector equals u. So there is an additive identity, associative. The zero vector, right, just has zero for all of its components. We have an inverse. It's additive inverse. These properties are going to be useful for us when we get into our next section called vector spaces. So that's kind of why I'm going through these. C times u is going to be a vector in the plane. So that's closed under scalar multiplication. And so if I multiply by a scalar, it stays a vector in the plane. If I start with a vector, multiply by a scalar, it stays as a scalar. And then we have some properties here for scalar multiplication. We have a distributive property. And we have the other kind of direction for this distributive property as well. Well, we can do it with scalars as well. Cu plus du. So notice the difference here. These are two different distributive properties. Here we have two scalars we can multiply by two vectors we can multiply by a scalar. Here we have two scalars and multiply by one vector. Right? So in either case, we can distribute those. We also have associative property here with scalars. Right, and then I can multiply by the scalar first, or multiply those two scalars together and multiply by the vector. These are all things that we would naturally, I think, do with these, but as we enter into some more unusual operations and spaces, a lot of these things are certainly not guaranteed with other kinds of operations. So you might be thinking to yourself, well, of course, if you add something and it's negative together, you should get zero. But that really depends on how those things are defined and if we really have those objects within the new framework that we're working in. So the sort of overall goal here is to look at new sets or collections of objects and figure out how those objects all interact and work together. And when we do that, we're going to learn how some of the properties that we can show in one grouping are then going to apply to all of these different groupings. So while these are sort of natural properties for us because it's a new kind of object, they're not certainly not guaranteed. The last one, which I kind of just ran out for, number 10, is that we have a multiplicative identity with a scalar. Identity. Scalar, and here we had, those are my distributive properties. Here we have the associative. It's a scalar. So we have these kind of 10 properties of vector operations. And I think you could imagine, like I said, how we could prove some of these just based on our original definitions of what scalar multiplication is and what vector addition is. I won't go through those proofs. They do a couple in the book, but they follow pretty directly because of our already properties of real numbers. Now we can extend these ideas. We've been thinking about these probably in terms of R2, but we can also look at other spaces. So not just the plane R2, but R1, R2, R3, R4, right, etc., up to Rn. These are all different spaces. So R1 is just a set of real numbers, one-dimensional space, right? R2 is the plane, right? So these are ordered pairs. R3 is ordered triples. That's like space, right? 3D space. R4, we can just keep going with this. Geometrically, we can't really process that, but mathematically, it's not a problem, right? We can do all the same kind of operations, negatives and positives, and scalar multiplication with all of these different spaces that we have. And you'll see these all have the same 10 properties as R2. So you'll see there's some different operations that you'll have to do maybe in the homework, but I think they'll all be pretty straightforward. We do have the additive identity, which we represent with the 0 vector. And the additive inverse we represent with the negative. So, those are sort of special vectors, right? Given the situation. I guess one thing to note here, this is a unique value. In other words, if you add V and something else to get V, then those things must actually be the same things, right? In other words, you can't have two different values that are the additive identity inverse, right? And remember what the inverse is that if I add the two quantities together, right, I should get the 0 element. That's what it means to be an additive inverse. What I do think is a nice connection here is to look at what's called a linear combination of vectors. And the idea is that we would like to be able to take and write a vector, say x, as some combination of these other vectors. We've seen this before with matrices. That's the same idea with vectors. So these are scalars. Right, so I want to be able to write my vector, my given vector, as a linear combination. So that means adding scalar multiples of these other vectors together to create that quantity. So for example, if I give you, let x be the vector 3, 2, we'll just work in R2 here. And V1 equal the vector 1, 3, V2 equal the vector 2, 1. Can we write x as a linear combination of V1 and V2? And so what we would do there is to say, well, can I get 3, 2 to equal C1 times 1, 3 plus C2 times 2, 1? And from what we know about vectors, that's only going to happen if those corresponding components are equal. So 3 has to equal C1 times 1 plus 2 times C2. And 2 has to equal 3C1 plus C2, right? And here, right, this is a system, and we can certainly solve this system for C1 and C2, which will then give us that linear combination. And once we find C1 and C2, we have then the linear combination that equals that. one other note, I mean, you might notice this is very, very similar to the work we were doing with matrices. And in fact, we can really write a vector as either a column matrix or a row matrix. And what I mean by that is we've been writing them as sort of these ordered pairs, but I can really think of it as just a listing of elements. And vector addition and scalar multiplication and all those things are going to work the same, whether I think of it as each vector as a series of columns, or whether I think each vector as a series of rows. So it's sort of like whichever is convenient for us, we can think of the vector u, right, as being u1, u2, all the way to un, right? Or, right, u could be thought of as u1, u2, all the way out to un. So what that's just saying is that if you see that notation, don't worry. The way the vector operations that we do are going to be equivalent, whether we think of them as row matrix or a column matrix, with addition and scalar multiplication. So sometimes we'll find this more convenient, and sometimes we'll find this more convenient, and sometimes we'll think of them as just points in the plane, but they're all connected to this directed line segment. Okay. And also, of course, they all follow those 10 properties of vector operations. All right. So that's the start here of just getting a little bit of comfort with vectors. I hope it's pretty straightforward. We know how points in the plane work, and a lot of this is with R2. There's a little bit of notation here, right? Keeping track of scalars and vectors. Those are different types of objects. And it is important to go back and really reference these 10 given properties. So if you're trying to show something is true using vectors, we have to sort of base it on the rules that were given. It's the same with numbers. We're just very comfortable with numbers because you've been working with them for, however old you are, 15, 20 years, right? You've been working with numbers, and vectors are new for us, and they don't have all of the same properties. So if you're going to try and show something is true, right, we'd like to go back and show that it's based on some of these, all of these properties here. All right, so the next section is vector spaces, and I think that's where we really start to see, I think some real interesting properties and relationships that's going to kind of stay with us for the rest of the course here.